We will now look at another type of data setup, and that's called grouped interval data. Some time ago, people thought that grouped interval data would disappear, but with the advent of the internet and more and more types of surveys online, there is still a very big use of intervals. That is, some data is not collected in raw format. For example, if you're filling out a questionnaire either online or on paper, it's quite common for them not to ask for your age, but for them to ask for your age within a certain interval. All right, they may not really care if you're 26 and a half. They might just say, are you within 20 to 30, etc. Okay, so that's grouped interval data. Okay, so this is data in intervals. But of course, when we have data in intervals, right, for instance, for example, age 20 to less than 30 years, right, is an example of an interval. But when we have data in intervals, we lose some information. Okay, but that's not so important in the long run. Remember, usually we have a sample, and a sample is not a precise reflection of the population. In any case, there are all sorts of approximations going on, and some approximation or loss of data is not that important, especially when it helps us sometimes visualize the data. Alright, it turns out that the formulas that we just used for the grouped integer data we can also use for the calculation of the average and variance, and therefore standard deviation for grouped interval data. We will also show how to calculate the median from such data. Alright, so in this movie we're going to show how to calculate for the grouped interval data the average, the variance, and of course standard deviation, and now the median. Remember, since I've said that when you group data into intervals, you lose some information, all of these calculations will be slightly inaccurate. If you had the raw data, you could get more accurate information. Also, if you decide to use different intervals, you'll get slightly different numbers. Okay. To find the following data set, call this 1G. They're integers, but they're all over the place. So let's just write them down, and then we'll deal with it that way. Alright, so across the top we have 18, 36, 31, 11, 15, 4. Next line. 22, 29, 25, 9, 7, 8. 46, 58, 20, 12, 36, 19. 33, 62, 18, 24, 13, 15. Now this is raw data, but I'm going to show you how we would put the raw data into interval form. Alright, when we make intervals, alright, we like to have between 5 and 8 intervals. And you want to make your intervals sort of useful and easy to handle. Alright, that's why the 5 to 8. The human mind can handle that many, up to 8, any less than 5, and we sort of squash the data too much. Alright, so in this case, it's maybe a useful exercise to talk about the range of the data. You go from the highest to the lowest. Alright, the highest data point, the largest data point is 62, the lowest is 4. So the range is 58. So if we divide the range by 5, you get approximately 11.6, and of course we don't want an interval of exactly 11.6 because it's just too difficult to handle very well, but anyway, we can come close. Range divided by 8, 58 divided by 8, it's about 7.25. What's a nice number close in that range? Well, a nice number close in that range is 10. Okay, so if we make intervals of a width of 10, everything would be good. So for example, we can go 0 through less than 10, 10 through less than 20, etc. Right? It's a lot easier than going 4 to 15.6, and from 15.6 to whatever. You know, that's too hard to handle. Alright, so let's tabulate our data in that form. Alright, so I'm going to write down these intervals. And you'll notice that I'm using intervals of all the same width, and for most applications that's the most useful. But I'll also show you later how to deal with intervals with unequal widths. Right? For most things that we're going to do here for calculations, it really doesn't matter if the intervals have the same width or not. But of course, if you're going to look at these intervals and try to make sense of them, it's a lot easier just to have them the same width. Alright, so I'm just going to tell you what the frequencies are. Alright, there are 4 numbers between 0 and 10, not including 10. Hopefully that you will check these numbers to make sure that these are the same numbers that you would get. Alright, to do our calculations, we'll need an X. So at this point we don't have an X. By the way, the first 2 columns, right, that is a frequency distribution again. The X's will be the midpoints for our limits. So from 0 to 10, right, midpoint is 5. From 10 to 15, 10 to 20 is 15, etc. Alright, to do our calculations for the average, we need a column for fx, and then to do a calculation for the variance, we need an fx squared. Alright, and so fx column f times x is 4 times 5 is 20, 8 times 15, 120, 5 times 25 is 125, 4 times 35 is 140, 1 times 45, 45, then 55, and 65, 65 that is. Fx squared, 4 times 5 squared is 100, 8 times 15 squared is 1800, next one 31, 25, 4900, 2025, 3025 and 4225. Alright, make sure that you can duplicate those answers. Then we're going to add some of these columns. Again, we're not going to add the x's since we have frequencies here. So sigma f, some of the frequencies is 24. It's also the number of data points. Sigma fx is 570, and fx squared 19,200. Okay, and once we've got to this point, then the calculations are identical to those for grouped integer. So I'm going to go to the next page and rewrite that information. Sigma f 20, sigma fx 570, and sigma fx squared 19,200. So x bar, the average, sorry, let me put down what we're calculating here. Sigma fx divided by sigma f, and sigma fx is 570 divided by sigma f is the n, the number of data points, 24, and that boils down to exactly 23.75. It's also 4 significant places. Right? When you get an average or an answer for the average, make sure it makes sense. Okay, we have numbers going from 4 through 62 in our frequency distribution. We have a lot of the data points, most of the data points between 10 and 20. So you'd expect an average in that range, all right? And that's what we do. We have an average close to 20. Variance s squared sigma fx squared minus n times x bar squared divided by n minus 1. Alright, sigma fx squared is the 19,200 minus n. Remember, the 24, the sigma f is also the n, times x bar, it's 23.75 squared, divided by the n minus 1. Okay, and that works out to be 246.2 to 4 significant places. And so the standard deviation, S being the square root of that, and again to 4 significant places, that's 15.69.